Now that we've taken a look at how to solve log and exponential functions, we want to look at how would we ever really see these type of functions in any type of an application? Where would they come up? The easiest place to look at for me is money, right? There might be some jobs that you see different things in, but everyone deals with money. So the first scenario that we might see an exponential function used in is this idea of interest. So we can look at compound interest formulas, which are used in any type of a savings account or savings formula, all right? Again, this is going to be simple interest and things like that. So I'm not going to use some huge formula. We're not talking about an amortization formula. We're not talking about any kind of credit card or things like that. But what we are talking about is being able to look at a most basic exponential formula and see its application and actually use it. So in this first equation that we have, this is going to be our compound interest formula. So I've got all of the different elements here listed. So you can see the capital P is the principal or initial investment, R is the interest rate. One thing to be said about the interest rate is that it's written as a percent. So say we have 48% interest, then it would be written as R equaling 0.48. So when we look at our interest rate and we look at plugging into R, we want to move that decimal twice, right, because of the percent sign. Then N is going to represent the number of compounds per period. So what that means is this is going to be some sort of a word, meaning something like, say, if it says annually, I'll use N to equal 1. If it says semi-annually, then I will use N to equal 2. Let's say it says quarterly. Then I would have my N to equal 4. We could have monthly, which would mean N would equal 12. And then you could have bi-monthly, which would be N equaling 24. The T is going to represent the number of years. Make sure that it is years, right? So if they give me months, I need to convert it to years. And then A is going to be amount that it's going to grow to. Okay, so what we want to do is we want to identify the different variables, plug them in, and then see how we might want to solve. So looking at this first example here, it says we want to find the value of an investment of $5,000. So I'm investing $5,000. That's going to represent our P. So our P is going to be $5,000 at a rate of 5.75. All right, so that means R is going to be 0.0575, right? Remember, I moved that decimal twice. It's compounded quarterly, so my N is going to represent 4, because that's 4 times per year, and then for 8 years. So now that we've got all of our different elements here, all of our different variables, we're going to plug it in and then see what we need to do to solve. So I'm just going to plug straight into my formula. I'm going to have 5,000, parentheses 1 plus 0.0575 divided by 4 raised to the 4 times 8. So that means we must be solving for our A. So one thing that you want to do is make sure that whatever calculator that you are using, say to take the exam or anything like that, you can type it in and get the same exact answer. So when I go to type it in, I need to make sure that I'm typing it in correctly. So I should get $7,894.47. Since it's money here, we're going to round to 2 decimal places, or the hundredths place. So plugging in should be super easy. Make sure that you are typing it in using the correct syntax or whatever in your calculator so that you're getting this answer. All right, so let's look at the next example here. So it says we want to find the initial amount of an investment after 4 years at 3.5% interest rate, compounded monthly, to be $3,250. So let's see what we have here. We want to find the initial amount. So we do not know what the P is. We do know that the T is 4 years. The interest rate is going to be 0.035. Remember, we're moving that decimal. It's compounded monthly, so my N is going to be 12. And then it has grown, so my final amount, my A, is going to be 3,250. So let's plug in what we have here. So we have 3,250 equals P, 1 plus 0.035 divided by 12 to the 12 times 4. All right? So if I look at this equation, when I look at all of this here, this is just one number plugged into the calculator. So the first thing I would do is plug all of that into the calculator. I would get 3,250 equals P times, and when I plug all of that in, I'm going to get 1.15. What I need to do then is just simply divide by that 1.15, all right? So again, making sure that I can plug that in, get the correct answer, and then finish solving. So my my initial investment should equal $2,826.09. Again, rounding to the hundredth because it's money here. All right, so that's going to represent our compound interest formula. The next formula that we want to look at, that's going to be our continuous compound interest. So I'm going to see some very similar variables here because it's still talking about a compound interest. However, this time it's continuous. So what I will not see here is the N. So I'm not going to have any N because what number would we use for continuous? We would use infinity, which does not make sense to go plug in a number for. Whereas when we just had regular compound interest, there was an amount of times, a specific amount of times, that N that we were plugging in. This time, since it's continuous, we're going to use a different function. We're going to use the E function. This E is actually the exponential base, right? So it's not a variable that we're going to plug into. It is the number E. So E is roughly about 2.71, and then it keeps going, very similar to pi, right? So that is just a number there, okay? I would still be looking for the P, which is my initial, the R, which is the rate, still remembering to move the decimal. The T is still the number of years, so making sure that I'm in years, and then A is still the final amount. So let's see what it might look like here. Let's look at this first example. Okay, so it says I'm going to deposit $2,000, so my P is going to be that $2,000. All right, it's compounding continuously. All that means is that I'm going to be using this formula versus the last formula. I've got an interest rate of 4%, so that R is going to be 0.04. And then I want to know how much I'll have in 3 years. So my T is going to be 3 here. All right, so let's go plug in and see what we've got. So I've got 2,000 E, which is the number E, raised to the 0.04 times 3. So I'm looking for that final amount. Now remember, this E is just a button in your calculator. So I'm going to need to type in, most of your calculators will either have E or it will have E with a little caret key. All right, so make sure that when I type this in, that 0.04 times 3 is in the exponent of E. So when I go type this in, again, making sure that you're practicing with whatever calculator you're going to be using for the exam here. When I go plug that in, I should end up getting $2,254.99. Okay, last example, it says, how much will you have to invest if you need $12,650 in 5 years and your account is compounding continuously at a 2.65% interest rate? So let's see what we have. I'm going to need in the end 12,650. So that's going to actually be my final amount. It's going to represent my A. I have 5 years, so that T is going to be 5. It's compound and continuous, so that just means that I get to use this formula. And my rate is going to be 0.0265. All right, so we are looking for our principal amount. So let's plug it in and see how we can solve this. I'll start off with that 12,650 equals P e to the 0.0265 times 5. Now, just like we saw before, this e to the 0.0265 times 5, that is just a number in your calculator. So I'll plug that into my calculator, and I'll get roughly 1.14, okay? Then that's what I'll divide, 1.14. And so my principal amount should end up being about $11,077.06. So again, making sure that we can plug that in and get our correct answer using our calculator, right? So now we've seen how we can use this exponential type of function in kind of a real world application. The other application that we want to look at is this idea of exponential growth and decay. So when we look at an exponential growth and decay model, we can see this in lots of different areas. Most of the time it's going to be some sort of a scientific application. Okay, now for us in this course, they will give us a formula already written. They might still need us to plug in variables, but it won't be something that I'll need to already know the formula for. Unlike the last two that we looked at with the compound interest and the continuous compound interest, those I'll need to be familiar with those formulas because they may or may not tell me what they are. They might just say that it's compounding continuously, and I'm going to have to know what that formula is. However, when we're looking at exponential growth and decay, they will give us a model to either plug into or to use. Okay, so let's work through these and see if we can solve them. Again, they are all exponential. The only difference here versus when we were looking at our kind of money applications is that here I could also have decay. Now, even though money does decay, obviously, we are not going to look at those in this course. So when we look at exponential growth and decay, it will be a model that they give us. When we're looking at money, it will always be an increase or a growth. Okay, so let's look at this first example. It says in the exponential model, b equals 18.92 e to the negative 0.009t. It describes the population of country B, beta, in millions after t years after 2000. What will the population of beta be in 2015? So let's look at what they gave us. The only variables that I'm looking for is either going to be t or b. Now they told us that t is going to be years after 2000, and they gave us a year of 2015, right? So when I look at that, that means they're giving us a t of 15 years, okay? So what that means is that I can go plug in, and I must be looking for b because that's the only variable that I have remaining. So I'm going to go plug in to my formula here, that 15. And again, this is just typing straight into the calculator, and I should get roughly 16.53 million people. All right. So again, making sure that I can type that in and get the correct answer there. Okay, let's look at example 2. They give us an exponential model, and it's going to describe the population of Japan, which is RA, in millions T years after 2003. And they want to know how many years after 2003 will the population reach 130 million. So this time they want to know how many years. So they're looking for t, which means they've given us our a, because remember there's only 2 variables remaining. So they've given us our a and they're looking for t. So let's do it. I have 130 equals 127.2 e to the 0.001 t. Now, this one's going to take a little bit of solving, so I have to think about how did we solve exponential equations? Well, when we had an exponent on one side, what we were going to do is we were going to isolate that exponent. Then we were going to use a log function instead, and then we were going to finish solving. So let's do that here. So I'm going to isolate that e. To isolate that e, I'm going to need to divide by 127.2. Okay, when I do that, I should get 1.022 equals e to the 0.001 t. Okay, so now that it's isolated, I need to use a log function. So I would take the base of that e. Now remember, the base of e is a specific log. It's that natural log. Remember that e has a base for a natural log. So when I look at this one, I'm actually going to introduce a natural log. I don't need to put the e, but I could. And remember, I'm going to switch these two values. So it's going to be of 1.022 equals 0.001 t. Now, this natural log is a button in the calculator, so I don't need any change of base or anything like that. I'm just going to type that straight into the calculator. And when I type that into the calculator, I should get about 0.0218. Okay, and that's going to equal 0.001 t. Then I'll divide by 0.001. And so my t would be about 21.8 years. So how many years after 2003? It would take me 21.8 years for the population to reach 130 million. Okay? So let's try one more example to make sure that we understand how to do these exponential growth and decay problems. Okay, this says the population of country Delta was 19.19 million in 1992. 14 years later, in 2006, the population was 25.86 million. The exponential growth function, they give me a function here, describes the population of country Delta D in millions, t years after 1992. And we want to find the k. So they are telling me which variable to find, which means they must have given me a t and they must have given me d there. All right, so let's see what we have. So they've given me 25.86, which would be that capital D. Then I'm going to use my 19.19 e to the k. They did not give me, remember that's what they're asking for. And so the t they must have given me, it says 14 years later. So that'll be my 14 there. Okay, so this looks exactly like the last problem. We want to go through our steps again, right? We want to first isolate the exponent. We want to use a log. In our case, that log is going to be a natural log because we've got an exponential growth and decay is going to be that e. And then we want to solve, all right? So let's do it. I'm going to first divide by that 19.19. That's going to give me about 1.348. And make sure when you're in my math lab, you're rounding to whatever they're asking you to round to as you're going through here. All right, so now once I've isolated that base, that e, I'm going to introduce a log. More specifically, I'm going to introduce that natural log. Okay, so I introduce my natural log, which means I'm going to now switch these. So it's going to be natural log of 1.348 equals k times 14. So I'm going to go to my calculator, right? I can type that natural log straight in. I don't need any change of base. And after I do that, I'm going to divide by that 14. So I type it in, divide by 14, and my k should end up being 0.0213. If they want me to write it as a percent, then I would say it would be 2.13%. So either of these options, if they want just the k value or if they want me to write it as a percent. So now we've seen another type of model that we can use, still being able to solve and manipulate these exponential functions.